we'll be talking about functions and continuity. So in this section we will first define continuity. We already know what functions are, so you don't need to find that. We'll talk about continuity of rational and piecewise defined functions. And lastly, we'll look at graphs of continuous functions. So continuity, what is it? Intuitively, we say that a function is continuous if its graph has no breaks or jumps or gaps or anything like that. So our example here on the left is an example of a continuous function. Right? It's nice. There's no gaps. You could draw it without lifting your pencil off the paper. The function on the right, it has a jump here and then a hole here. So both of those, this jump and this hole, lead to this function being not continuous at those different x values. Notice that you could not draw this without lifting your pencil off the paper, in fact, in two spots. Okay, so that was our intuitive definition of continuity. Here is the actual definition of continuity. So if I ask you what is the definition of continuity, this is what I'm looking for. Don't say what we said on the last slide. So what is that? So we say that a function f of x is continuous at the point x equals a if the following three conditions hold. So it's a three-part thing, right? Part one, f of a is defined, right? So that means you can plug a in and the function will spit out a value for f of a. Part two is that the limit as x approaches a of f of x exists, right? So the limit has to exist. And part three is that the function is defined to be the same thing as what the limit is, right? So the two things you got in parts 1 and 2 are the same, right? So function has to be defined, the limit has to exist, and those two things have to be equal. If I ask you to show whether or not a function is continuous at a given x value, you have to check all three conditions. So you should think it's a three-part process of doing all parts of this definition. It says discuss the continuity of this function, this piecewise defined function, at the point x equals 5. So let's first just review what a piecewise defined function is, right? So what this means is that f of x, if you're plugging in values less than 5, it's going to spit out 2x minus 1. So for example, if you plug in 0, 2 times 0 minus 1 is negative 1, so f of 0 would be negative 1. That's true for any number less than 5. It would spit out 2x minus 1. Right? It says for all x values greater than or equal to 5, it's going to spit out 14 minus x. So if you plug in 10, it's going to spit out 14 minus 10, which is 4. If you plug in 5, it's going to spit out 14 minus 5, which is 9. Right? So that's how this piecewise defined function works. Sometimes it'll be three pieces where instead of having an or equals, it'll split up the less than and the greater than and the equals all in three different pieces. Sometimes it'll be like this. Either way, it just tells you for whatever x values, this is what the function spits out. Okay, so now let's talk about continuity. So we're discussing the continuity. Another way to phrase this would be, is this function continuous at x equals 5, right? So if we're talking about is this function continuous, three-parter. Step 1, can you plug 5 in? So what is f of 5? Well, over here is where it says what to do. If you're plugging in x equals 5, and so that would be 14 minus 5, which is 9. So for part 1, can we plug 5 in? Is the function defined? Answer is yes. Part 2, we need the limit as x approaches 5 of f of x. Right, so how do we find the limit of a piecewise function? Well, we need to take the limit from the left and see if it's the same as the limit from the right. So what's the limit from the left of f of x? Well, since we're coming from the left, we're going to use the top line right? The left is values less than 5. So the limit from the left of f of x is the same as the limit from the left of 2x minus 1. And now remember, to take limits, we just want to try to plug in. So what's 2 times 5 minus 1? Well, that's 9. So the left-hand limit was 9. We also need to check the right-hand limit, or the limit from the right. So the limit from the right, that's numbers x values greater than 5. So we're going to use the second line here, where it says x is greater than or equal to 5, and for that we're going to check the limit as x approaches 5 from the right of 14 minus x. Notice that I kept writing my limit symbol here and here because I had not taken the limit yet. And then over here, once I did take the limit, I stopped writing that. So again, I'm going to take the limit now and plug in x equals 5. So I'm going to stop writing the sign that says to take the limit because I just did that. And I get 14 minus 5 is 9. So, since the left hand and the right hand limits are the same, the actual honest-to-goodness limit as x approaches 5 of f of x is 9. So there, the limit exists, it's 9. Step 3, you would say, since f of 5 is 9, and that's the same as the limit, those are the same, so this function is continuous. So those are the same, so f of x is continuous at x equals 5. And there you go. We're going to do the same process every time we're checking continuity. Step 1, is it defined? Step 2, find the limit. And step 3, are those things equal? If any of those do not hold or are not true, then you would say the function is not continuous. So if you can't plug in 5 in step 1, you would immediately say the function is not continuous. If this limit did not exist in step 2, you would immediately say the function is not continuous. Or in step 3, if these two things were not equal, you would immediately say the function is not continuous. All right, here's another one. Notice we still have 2x minus 1 and 14 minus x, but this symbol has changed, right? Instead of being an or equal, it's just a greater than. So let's discuss the continuity at x equals 5. So step 1 of discussing continuity, step 1 of the definition of continuity is, what is g of, wow, that's not a 5. That was pretty bad. Let's try again, see if I can write a 5. G of 5. That's almost better. Anyway, can we plug 5 in? Well, there's nothing over here that says what to do for x equals 5. So that means that g of 5 does not exist. And that means that this function is not continuous. And if it fails any one of these 3 steps for continuity, it is automatically not continuous. So f of x is not continuous at x equals 5. All right, here's another function. It's 2x minus 1 and 3 minus x. So again, we want to discuss the continuity x equals 5. So step 1, can you plug 5 into the function? So what is h of 5? Well, we're going to use this for that because that's the or equals. And so that's 3 minus 5 is negative 2. Step 2, we need to find the limit. So what is the limit as x approaches 5 of f of x? To find that, we'll need to do the left hand and the right hand limits and see if those are the same. So let's check the limit as x approaches 5 from the left of f of x. Coming from the left means that we're talking about values that are less than 5, so we're going to use the top line. So this is the same thing as the limit as x approaches 5 from the left of 2x minus 1, and that is 2 times 5, we substitute in x equals 5, minus 1, that's a 2 there, and that's 9. So the limit from the left was 9. What about the limit from the right? The limit as x approaches 5 from the right of f of x. So we're from the right, so that's x value is greater than 5, so we're going to use the second line here. And so we want the limit as x approaches 5 from the right of 3 minus x. So we're going to substitute in x equals 5, and 3 minus 5 is negative 2. So we got negative 2 for the right-hand limit and 9 for the left-hand limit. And so since those are not the same, this limit does not exist. The limit as x approaches 5 of f of x does not exist. So since we fail step 2, this function is not continuous at x equals 5. It's not continuous at x equals 5. All right, here's another one. Notice this is the exact same function as I just had, so I already know it's not continuous at x equals 5 from before. So from before, not continuous at x equals 5. Now, what is different here? Well, instead of saying, is it continuous at 5, I said over the interval from 4 to 6. Well, what does that mean? So to be continuous on an interval means that you're continuous at every point in that interval. So since 5 is in that interval, h of x is not continuous at 5, and so it's not continuous on the interval. Right? So we would say here h of x, so since it's not continuous at 5, and 5 is in here, since 5 is in the interval from 4 to 6, that means that h of x is not continuous on this interval from 4 to 6. Right, so again, to be continuous on an interval means you're continuous at every x value in that interval. So since we're not continuous at x equals 5, we're not continuous on the interval from 4 to 6, or any other interval that contains x equals 5. Continuity of polynomials and rational functions. So first off, polynomials are continuous everywhere for all real numbers. No matter what you plug in, if you have a polynomial, it's continuous at that x value. Rational functions are continuous only for the x values that make the denominator not equal to 0. Another way to say that is that they are not continuous only at the x values where the denominator is 0. So, discuss the continuity of f of x is 3x squared minus 100. Well, that's a polynomial over the real numbers. So, where is this function continuous over the real numbers? It's continuous everywhere because it is a polynomial. All right, it's a polynomial. All right, here we have g of x. That's not a polynomial. It's a rational function. So we need to figure out when is the denominator equal to 0. Well, that happens at x equals negative 2 and x equals 4. So g of x is continuous on what intervals? Well, as long as you don't have negative 2, so to say not negative 2 is negative infinity to negative 2, and then we're going to skip over negative 2 and go all the way up to 4, and then skip over 4, go all the way up to infinity. Another way to say this is to say g of x is not continuous only when x equals negative 2 or x equals 4. So again, for a rational function, It's continuous everywhere except when the denominator is equal to 0. Okay, now let's look at graphs of functions, right? So I'm going to say, is the function that is graphed continuous at x equals a? So is this function continuous at x equals a? No. If not, why not? So here I want to reference the definition of continuity. So for this guy, if I look at the limit from the left and the limit from the right, those are not the same. So this limit does not exist as x approaches a. So it's not continuous because the limit does not exist. All right, how about this guy? Is this function continuous at a? Again, no. And here we have a hole at a, so f of a does not exist. So this fails step 1. This guy, where the limit does not exist, failed step 2. All right, how about this example? Is this continuous at x equals a? Well, it's defined there. The limit exists, and those are the same. So, yes. And that's 1.5. There's the homework, and there's Penny Girl. Rest in peace.